Hello and welcome everybody. Today in geometry, we are starting a new chapter, and this is going to be on trig ratio. So this is kind of like an introduction to trigonometry, and it's basically kind of like, if you were to look at algebra 1 and algebra 2 as, like a sequence right there, then geometry and trigonometry would then be a sequence, because then that's where you're going to apply all the stuff that you learned in geometry into something that is more applicable, or something that's a little bit more advanced. So anyhow, this is what this section is about, or this entire chapter is about. So let's go ahead and get started then. So first, we're going to have to define a few terms that are going to be very essential for trigonometry. And these terms are what is known as the trig ratios: sine, cosine, and also tangent. So sine, cosine, and tangent. Now, the way it works in the definition is that if you have any right triangle, we'll go ahead and call it A, B, and C, and you can see the illustration over here on the right hand side, where B is going to be my right angle. Then by definition, the sine is supposed to be represented as the ratio of the opposite over the hypotenuse. Cosine of an angle is supposed to be the represented as the ratio of the adjacent over the hypotenuse, and then tangent is supposed to represent the ratio of the opposite over adjacent. Now, in terms of sides, I'm going to go ahead and write that down in just a little bit. And the reason why I don't kind of like, fit it in here in this triangle is, well, sine, cosine, and tangent are different depending on which angle you're actually looking at. So here in this first case, let's say that I am looking for the sine of angle A. Now, sine is shorthanded into SIN, so that's that's sine right there. So sine of angle A. Now here is angle A then. Okay, we're looking at it as a ratio of the opposite side and also the hypotenuse. The opposite side over here, well, let me go ahead and label them using different names if you want. So let's go and call this little a. Let's go ahead and call this little b right here, and let's go ahead and call this little c over here then. So in terms of your ratio, sine of angle A, the opposite of angle A is going to be the lowercase a as a side, divided by the hypotenuse, which is always going to be the same, which is going to be b in this case. Whereas if I say the cosine of angle A, then that means by definition is supposed to be the adjacent side divided by hypotenuse. So angle A's adjacent side is going to be side that is going to be length of C, divided by the hypotenuse, which is going to be the length of B. And finally, for tangent, that is supposed to be the opposite over adjacent. So that means that the opposite of angle A is going to be side A over the adjacent of side A, which is going to be side C over there. Okay, so you can see how if we're referencing this as angle A, this is going to be the opposite, and then this is going to be the adjacent, and then this is always going to be the hypotenuse. Now, if we were to use a different angle as a reference, because technically I can also say the sine of angle C. Okay, I can also say the sine of angle C. So if I were to say what is the sine of angle C in this case, now we're going to refer to this angle, and that's where things are going to be different. The opposite of angle C is now going to be over here, because that is going to be the opposite of this angle right there. Whereas this side right here, this is going to be then the adjacent, and then the hypotenuse will still be the same thing. So that's the reason why I didn't write sine of what angle, cosine of what angle, and so forth. But anyhow, going by again the formal definition, the sine of angle C will then be the opposite over hypotenuse. So that means it's going to be C divided by B. The cosine of angle C is going to be the adjacent over its hypotenuse. Its adjacent, angle C's adjacent, is going to be A, and then divide by hypotenuse, which is going to be B. And then finally, for tangent of angle C, that is going to be then equal to the opposite over the adjacent. So that means that it's going to be C over A in this case. Okay. So you can see, when you first refer to a trig ratio, you have to take the trig ratio of an angle. Okay, so an angle actually has to be involved. So you can't actually just say sine or cosine or tangent. It has to be a sine of an angle, tangent of an angle, or cosine of an angle. Okay. And in terms of like the sides that it's referring to, it's always best to refer to like what is the opposite, hypotenuse, and also the adjacent, rather than the actual side, because you could be referring to a different angle that you don't, and somebody else might be looking at a different angle as well. So That is going to be our formal definition in this case, okay? Now, can you actually take the sine of angle B, cosine of angle B, and tangent of angle B? The answer is yes, you can get numerical values for those, but that is saved for a different section when we go beyond this. So for right now, we're always going to be looking at sine, cosine, and tangent of angles that are going to be complement, or actually it's going to be less than 90 degrees, okay? So we're not going to take any sine, cosine, or tangent of any angle that is beyond 90 degrees. Okay, now, so certain trig ratios, we actually know what they are. So what I'm trying to say is, for the angles of 30 degrees, 45 degrees, and 60 degrees, we've kind of studied them quite a bit over the past, couple of chapters or so, actually more than a couple of chapters. What I'm trying to say is I'm saying we actually know what is the value of sine of 30 degrees and also what is the value of cosine of 30 degrees. And finally, what is the tangent of 30 degrees? So those we're going to go ahead and reveal right now, so as to what they are going to be. Now, you can see on the right-hand side, there is a picture of a right triangle of a 30, 60, 90 inch triangle. Now, the way it works is, okay, in a 30, 60, 90 triangle, we say that there are special ratios that we can set up. The ratio is that if we say that the hypotenuse is going to be x, then that means the side opposite of the 30-degree angles is going to be half of that, so it's x over 2. And then the side that is opposite of the 60-degree angle is supposed to be root 3 divided by 2 times x. So that was the proper ratio according to what we derived in the past. And with that being said, we now can actually find out what is the sine of 30, cosine of 30, and tangent of 30. And this is always going to be true regardless of how big or how small those triangles are, because they're always going to be proportional. So as a setup for the sine of 30 degrees, once again, you can kind of refer to what is going to be the opposite, what is the adjacent, and so forth according to the angle. So here is my 30 degree. The opposite would then be this guy over here. So then that means it's going to be x over 2, because it's supposed to be opposite over the hypotenuse, right, by definition. So then that means it's going to be x over 2 and then divided by the hypotenuse, which is going to be x. So that means that if I clean up this ratio, sine of 30 is going to be the same thing as 1 over 2 then. So that is the first part. For cosine, we can do it the same way. Cosine is supposed to be the adjacent divided by the hypotenuse. So the adjacent to the cosine of the adjacent side to 30 degree, which is going to be this guy right here, then that means my answer is going to be root 3 over 2 multiplied by x, and then divided by the hypotenuse, which is equal to x. So with all the x's cancels out, then that means it's going to be root 3 over 2 numerically. And finally, for tangent, tangent is going to be the opposite, okay, divided by the adjacent. So then in this case, the opposite is going to be x over 2, and then divided by the adjacent, which is going to be root 3 over 2 times x. So here we might have to kind of like show the work just to see what this simplifies to. The x's, they are going to cancel each other out, so that part is good. So what's left is 1/2 and then divided by root 3 over 2. And when I flip the fraction right there to clean this up, we'll get 1/2 multiplied by 2 over root 3. So the answer is equal to 1 over root 3. Or for those of you guys that are asked to rationalize this, we're going to go ahead and multiply root 3 to both top and bottom. So my answer comes out to be root 3 over 3 then. So that is going to be the tangent of 30 degrees. And then cosine of 30 degrees and sine of 1/2. Sine of 30 degrees is equal to 1/2. Okay. All right. So that is going to be, those are, ratios that we actually know from here on out. So which is kind of good, right? We don't actually need a calculator for any of this. For the 45-degree angle, it's kind of the same thing. Here you can see I have a 45-degree angle, 45, 90, 45 triangle, isosceles right triangle. Again, what we can do is we can go ahead and say that, if one of the side is going to be x and one of the side over here is going to be x, then that means that the hypotenuse in this case is supposed to be root 2 and then multiplied by x then. Okay, we could work backwards or forward, doesn't matter, but it's always going to be this ratio. So if we were to do the same thing, let's go ahead and find out what is the what is the sine of 45 degrees. And then also what is the cosine of 45 degrees. And then finally also what is the tangent of 45 degrees. So putting everything in, let's see. We're going to go ahead and reference sine of 45 degrees. Since I have two of the angles that are 45, doesn't really matter which one I take. Let's go ahead and say that it's going to be this guy over here then. Okay, so that's going to be the 45-degree reference that I'm referring to. So this right here would then be its opposite. This right here would then be its adjacent. And then this right here would then be its hypotenuse. So we can kind of keep that in check for right now. So sine of 45 degree is going to be, once again, opposite over the hypotenuse. So then that means it's going to be x divided by x multiplied by root 2. So the x's will then cancel out, leaving you with 1 over root 2. And just like before with a tangent of 30 degrees, I'm going to go ahead and multiply root 2 to both top and bottom. So then we get a clean answer that is going to not involve the square root in the denominator. So my answer in this case is going to be root 2 divided by 2. Okay, so that's going to be the sine of 45. Cosine, well, cosine is going to be kind of the same thing, right? Because if you're looking at the adjacent over the hypotenuse, well, that's exactly the same thing as what's above, because the proportionalities are going to be the same thing since both the legs are going to be equal to x. So once again, it's going to be x over x times root 2, and I did the work right above it, so then that means that it can be simplified to root 2 over 2. Now finally for tangent is going to be the opposite over the adjacent. So the opposite over adjacent, that means it's going to be x over x. So that is equal to simply equal to 1 then. Okay, so there it is. Now we have the sine of 45, cosine of 45, and also the tangent of 45 degrees. Okay, and then now there's also technically the 60 degrees, but you know what? We actually solved for it already. So if I want to find out what is the sine of 60, cosine of 60, and tangent of 60, it would just be easier to reference back to this triangle because that's where we see the 60 degrees. Just to save a little bit of time, let's go ahead and just write that out. Okay, so let's say I want the sine of 60 degrees then. Okay, going back up into this triangle, this is now my angle of reference, right? And so this right here is now going to be its opposite, and then this right here is going to be its adjacent. So sine of 60 is going to be the opposite. So it's going to be root 3 over 2 times x divided by the hypotenuse, which is going to be x. So that means the answer is going to be root 3 over 2. Then if I solve for what is the cosine of 60 degrees, that is going to be equal to the adjacent. So that's x over 2 divided by the hypotenuse, which is x. So that would then give me 1/2. And then finally for the last one, for the tangent of 60 degrees, that is going to be the opposite over the adjacent. So that's root 3 over 2 times x divided by the adjacent, which is x over 2. So the x's cancels out, giving you root 3 over 2 divided by 1/2. So root 3 over 2 multiplied by 2 over 1. The 2's cancel out, so give you root 3 then. Okay, so those are your answers. Okay, so now, I mean, you know, this is all great and all with all these ratio and stuff, but I want to know, like, you know, how does this actually work out in terms of me solving for these right triangles? How do I use the sine, cosine, and tangent to solve for what is the measurement of a certain angle, or what is the side that's missing? Well, that's where the part underneath is going to be then, right here. Okay. Now we have to think about, okay, well, how does this work out with solving, right? What's the application to this? So unfortunately, because we only know how to solve for the 30, 60, 90 triangles, and also the 45-degree angles, we don't know anything about like all the measurement of the other angles, like what is sine of 17, or what is the cosine of 18 degrees, what is the tangent of 81 degrees, and so forth. That is where we have to use the calculator to use it as a reference to solve, because that's something that we cannot solve for by hand. But we can set it up at least, so then that way we can tell the calculator how to solve for it. Okay, so here are some problems with that then. So first one over here, I want to solve for what x and y are equal to, right? The lengths over there on the right-hand side of this right triangle. You'll notice what I gave you are, let's see, the hypotenuse and also the angle over there, which is 15 degrees. And I want to solve for all the missing sides in this case. Now, we can solve for the other missing angle right here, and that's an easy one because it's supposed to be the complement of 15, which is 75. But, you know, that's just something on the side. So let's go ahead and see if we can solve for the length of the sides then. Let's go ahead and solve for x, okay? So if I want to solve for x, I got to think about which trig ratio am I going to use. Well, I know the angle that's given to me, which is 15. I'm trying to solve for the side that is next to it, so that's the adjacent. And then we have the hypotenuse, which is 10. So if you're thinking about an angle with its adjacent and hypotenuse, the first thing that should come to mind would then be cosine. Because if you remember, cosine, right, of an angle is supposed to be equal to the adjacent over the hypotenuse. So in this case, referencing to cosine of 15 degrees, because that's the angle that's there, is going to be equal to the adjacent, which is x, divided by 10, because that's the hypotenuse. So there's your equation then. So now if I want to isolate x, then x is equal to 10 multiplied by the cosine of 15 degrees. And so this is where we're going to have to use a calculator to solve for this. So going over here, let's go ahead and move to the calculator. And I'm going to go ahead and solve for that for you then. Okay, so 10 multiplied by the cosine usually should be keys that are in the middle of the graphic of the scientific calculator. So push the cosine, and then I'm going to go ahead and give it the angle, which in this case is 15 degrees. Now, one thing you should make sure that your calculator is doing is that it has to be in the right mode. The mode that we're referring to is degree mode. So make sure it says DEG on top if you have a regular scientific calculator, not RAD, because RAD stands for radian, then that's something else that we'll learn in the future. But for right now, it's make sure that it's degree mode. So this is the mode that I need right there. So degree versus radian. So I'm going to go ahead and change it to degree right there. Okay. All right, so 10 times the cosine of 15 degrees, so that is equal to 9.659, okay? So 9.659, so that is going to be the length of that side then. So the side of x is going to be equal to 9.659, okay? All right, now that we have x, we can then go ahead and solve for y as well. Now, you have two options because we just solved for x, which is equal to 9.659. The option to solve for y is, well, you can either do another trig ratio or you can do the Pythagorean theorem because we technically have one side of the leg and also the hypotenuse. So you can say y squared is equal to y squared plus 9.659 squared is equal to 10 squared and solve for it this way. But you know what? Since we're dealing with this whole trig ratio thing, let's go ahead and keep it consistent. So let me go ahead and back up once again, okay? So now let's go ahead and kind of like circle what is it that we have and what is it that we want to solve for, just like before. So I'm going to go ahead and get rid of this, and then we're going to go ahead and get rid of this part over here, okay? I'm going to go ahead and use red this time, okay? Again, referencing to what we have. We have this 15-degree angle right here. We have to solve for the opposite side, so that's y. And then we have also as given the hypotenuse. So what deals with opposite and also the hypotenuse? Well, that's where sine comes in because sine of an angle is supposed to be the opposite over the hypotenuse then. So that means the sine of 15 degrees is equal to the opposite, which is y, divided by 10, which is the hypotenuse. So once again, we're going to go ahead and multiply 10 to the other side. So 10 multiplied by the sine of 15 degrees is going to be equal to y. So I'm going to go back to my calculator over here. So let's go ahead and put everything in. Let's see. So 10 multiplied by the sine of 15 degrees. And remember, make sure that's in degree mode, okay? So that's going to give us 2.588. So that's going to be my answer right there. So this right here is going to be equal to 2.588. And if you want to verify it using the Pythagorean theorem, then you can definitely do so, but I'm pretty sure that's going to be the correct answer, okay? All right, now for another variation of this, well, let's say this time I have the right triangle once again, and I'm given some sides, and I want to solve for the measurement of the angles, like say, what's the measurement of angle B and what's the measurement of angle A? Well, again, we can go ahead and set up some sort of a trig ratio to help us out over here. Let's say that I want to solve for angle B over here. Let's say I want to solve for angle B. Well, in terms of what's given, we have the opposite side, and then we have the hypotenuse. So if this is the opposite and this is the hypotenuse to angle B, then I can set up a sine ratio in this case, because again, sine is supposed to be the opposite over the hypotenuse. So we're going to say sine of angle B is equal to the opposite, which is going to be 5, divided by 7, which is going to be the hypotenuse. In terms of how do you solve for this, we can't do it by hand. We actually have to use a calculator. So this one, the way it's supposed to be set up is this. So if I want to isolate B all by itself, we have to do something to both sides algebraically. And that something is take the inverse function. So meaning how we are going to get rid of the sine then by taking the sine inverse. So in terms of like how do we write it? We usually write it as sine inverse of sine of B is equal to the sine inverse of 5 over 7. So note how I took the sine inverse of both sides. The left-hand side is just angle B, which is what I'm trying to solve for. And on the right-hand side, if I can solve for what's the sine inverse of 5 over 7, then we got our answer. And again, this is something that we cannot solve for by hand, so we're going to have to use a calculator. So we're going to go back over here to the calculator, okay? And be careful now, we're not doing sine of 5 over 7, we're taking the sine inverse. So you should see that exponent of -1, that means inverse then. So sine inverse of 5 over 7, 5 divided by 7, and we're going to make sure that it's in degree mode once again. So the answer is equal to approximately 45 degrees and 45.584, 585 I suppose, okay? So let's see. So let me go ahead and write that down. So that's approximately equal to 45.585 degrees. So that's going to be my answer. If we were to solve for angle A over here, we can do the same thing. But if you can see the sides that are given and also, the sides that are given, we're probably going to have to call for the cosine of the angles ratio, because cosine of angle A would then be equal to what's given right there, which is going to be 5 over 7. And then so that means A, the angle, is equal to the cosine inverse of 5 over 7, which again, you can go ahead and use your calculator to solve for. Your answer that you're supposed to get, well, let's go ahead and put it in just to see what it is. So over here, let's take the cosine inverse of 5 over 7. And that's equal to 44.415, okay? So 44.415. So this guy right here, the measurement of angle A is approximately equal to 44.415. And if you look at your two answers for A and B, right? 45 whatever for the first one, and then 44 point whatever for the second one, those two definitely should be complementary to each other, meaning that they add up to be equal to 90 degrees, and they definitely should. Okay, so there you go. That's going to be our answer. Now, the one thing that we do in math is that we don't really like looking at, not clean numbers, because this is what we call an irrational number, meaning it's a number that goes on forever, just kind of like pi. So we want to try to condense it to make it look a little bit prettier, okay? So the way we do that is we introduce something called degrees, minutes, and seconds. So here's how that works, okay? So if I take a degree right here, right? I want to convert it into something called degrees, minutes, and seconds. So this is kind of like what they call dimensional analysis in chemistry. What we do is we take the part that we don't like, which is the fraction part over here, okay? And then we are going to multiply it by a ratio. The ratio goes as the following. For every 1 degree, that is supposed to be equal to 60 minutes. Okay, so for every 1 degrees, that is equal to 60 minutes. So this right here means 60 minutes. Okay, that little dash up on the top. Okay, so the way it works is we're going to go ahead and take that 0.585 and then we multiply it by 60, right? Because the 0.585, that is in terms of degrees. So what I want to do is I want to convert that into minutes. And like we said, for every for every 1 degree, that is equivalent to 60 minutes. So that's why we're going to multiply by 60, because you can see that the degree parts are going to cancel out. So put that into your calculator, and we're going to get our answer, 0.585 times 60. So going over here, 0.585 times 60 then. So that is going to be 35.1. So in our answer, this is going to be equal to 35.1 minutes. So my final answer is going to be 45 degrees and 35.1 minute then. Okay, so that's kind of like a, like a nicer way of seeing it without having to write all that nasty decimal. And then similarly over here, we can do the same thing too. We can take that 0.415 and multiply by 60 to convert it into degrees then, or I'm sorry, into minutes then. So going back over here, 0.415 multiply, 0.415 multiplied by 60. So it's going to be 25, we would say actually in this case, right? So I think that's probably close enough. So this is equal to 25 minutes. So we will write that as 44 degrees and 25 minutes. And so once again, you can kind of see how with 25 minutes and then plus 35 minutes, that'll give you a total of approximately 60 minutes, which is equivalent to 1 degrees. And again, they should add up to be equal to 90 degrees then. Okay. All right.